reinforcement. That is the week number 8 this week. Now, weekly schedules. Here we are in the week number 8. And please have just a slight change. There is no face-to-face workshop in Bandura. Please note the Bandura students, you can join online workshop like this. I'm going online. We have it Bendigo one here, Bendigo face-to-face workshop, where I will going to help you with this one as well. Just give me now. So that's the one week number 8. Now, what you going to do it this week? So once you attend these lectures with me and workshop, you can explain the importance of providing adequate anchorage and development length for the reinforcement that you're going to you can explain it. You can differentiate between 2 types of anchorage failures that I will going to explain you. You can use AS3600 to calculate the development length and Laplant. That again, I will take you through the examples and some theory, and you can design the required bar detail to satisfy AS3600 development length requirements. So that is also one you can do it, and a recommended way to decrease the development length, some of the details which I will share it with you. So today I will talk about the introductions, development length, lamp length, and I will take one examples that can just back up the our theory. That's first 1 hour. I will take you through these topics, and then second 1 hour we will take the examples. As I mentioned, it's very simple topics, does not require so much technical details, but very important topics in terms of when you are going to do the when you're going to do the real job like in a practice. So reinforcement must be satisfactorily anchored or sufficiently developed, must be provided so that it can achieve the needed trace. So what happens here when you have a reinforced concrete beam here? Look at this beam. Look at this is a, let's say, beam, typical beams. Now on that beam you are going to apply the loads. Let's say you apply dead load, live load, and all these loads coming on to here. Right? Do you with me? Now, what happens here? The steel that is inside this concrete is not taking any load directly, because you are not loading the steel. You are loading the concrete, right? Steel is sitting inside the concrete, and we are not loading the steels. We are loading the concrete, by the way. When we load the concrete, how the steel going to get load? How you gonna carry? So then this bond comes into the play, that this concrete will transfer the load to the steel if there is an adequate bond, adequate adhesive bond between the steel and concrete. For examples, if you use only smooth pipe, let's say you put only those bar, simple bar, then you may not have the bond between the steel and concrete. If you don't have bond between the steel and concrete, you cannot generate this resistance of the tensile load that you are going to carry by the steels, right? Because the concrete will not going to transfer it. Concrete says, steel, I don't know you. We can't work together because we don't have that friendship. We don't have that anchorage. So for that case, probably I will show it to you if I can find it that road here. Okay, I found it. Now we found this one. Let me share with you with this one. So for here, you can see these ribs, right? Can you see these ribs? So we provide these ribs to have a adequate bond between the concrete and steel. It's frictions. You can see even I can hold it tight. If I have like this simple, I can slip easily. Concrete can't handle that, right? So between the concrete and steel. So if we have to place the rebar inside the smooth tube in a beam, the beam will develop no tension in the steels. So as I mentioned, there is no tension in the steels because the concrete and steel not going to work together. So we need to make sure that they work together. So we provide those ribs. To develop the tensile, we must contact or interact between the steel and concrete. So we must create this friendship. We must create this bond between the steel and concrete, then they to work together. So how are we going to make the steel and concrete work together? By making these ribs on the steels. Now, region where there is an excessive cracking may not provide enough interaction to provide development length develop the bar. So for example, let's say, what gonna happens here? We want to provide. So let's say, let me explain this one. So when you have a crack, when you load this one, what would be the bending moment diagram for this one? The bending moment diagram would be like this. This is the bending moment diagram. So in this region where the constant bending moments, you will have a flexural cracking. When you have a flexural cracking, um, uh, you will not have bond between the reinforcement and concrete. So what we need this bar to be yielded at this point. Yielded, that means point meaning it should carry all the loads that is required for us to carry. So how are we going to create the yielding? We provide the adequate length in the beam to provide this kind of so this is a development length that you want to provide the adequate development. You don't want to provide the length something like this, then these guys will gonna pull out, right? So you need to provide the adequate gripping. You need to provide adequate length extending from this point. So for example, let's say some engineers provide this bar here, and another engineers, let's say provide this bar at this length. So this guy here, they can easily come out and it will not create this yielding. It will not create this loading, that the tension resistance that still need to carry. So the standards will give you that you need to provide the adequate development length. Meaning that adequate development length in the concrete in a way that when you load the steel, it should yield at point where your concrete is cracked. So for example, let me put this one here. So let's say this is my Rio, and someone say that okay, I will not provide enough development length. So then I have only that much grip. Then I can easily pull out. Look at that. It's very simple to pull out, but someone provide adequate length, concrete is holding tight. It's very hard to pull it out. You can see because you have enough grip, enough development length to hold your steel bar. So at this point, when I pull it, it will going to yield. That's what we wanted. We want to yield that bar, right? I hope you understand that. So that is called development length. This length from this point to this point is a development length. That length that will hold the steel in the concrete when it's a crack, and that will create the yielding at that particular point where it's happened. So we need to design it. We need to provide the development length in a way that it will have enough grip in a general sense. I hope it makes sense. Now, if you don't provide the enough development length, this will happen. It will pull out. You can see it will pull out from the connection. So you can see not enough development length. So not providing sufficient development can lead to a catastrophic and brittle failure. So standard don't like it. It is a brittle failures. As I mentioned, the brittle failures is not like it. So again, I can explain you here. Hold it, not enough development length, bang, come out, no yielding, nothing else, no load carrying, and your concrete will just go into catastrophic failure. No ductility, enough holding, enough concrete, you can't pull it. You can look at that. You can't pull it, right? Enough development length, because the load will try to pull this one, and then this one holding it, then this bar going to yield, they will stretch, then it will reach the yielding point. So there is enough ductility. It will give you enough warning before it fails. Yielding means. All right. If the bar does not develop, steel will not reach the yield strength, and yield behavior of steel is not reinforced concrete structure for ductility. I already explained you that if you don't provide the enough development length, the bar will just gonna pull out, no yielding, no load, and you will have a failure. So now bond between the reinforcement and concrete is primarily provided by concrete bearing against the deformation in the resort. So as I mentioned, this is the tension force. Tension force equal to area times the stress, right? So area is whatever the cross section area of your bar, times by the yield stress, generally speaking 500 megapascal for the steel Rio. What gonna happens if you don't provide this bar? I already explained you. This is the development length, by the way. This is the development length. How much you going to put it inside the concrete, and this is concrete, by the way. If someone put very small development length, let's say like this, then you can easily pull it out with very small load. You will pull it out. Then if it is too small, then your stress is too small. We need to provide this length in a way that if you apply the tension force equal to ASFY, still intact. Still intact means still inside the concrete. It does not come out. How does it happen? Because as you know, this concrete which is inside here, they will create the resistance, this steel to not come out, because this concrete will going to try to hold these steel bars. If someone pulling it, then it will not going to happen. So let's say I will explain you this one here in this sense that if I have a concrete, let's say this hand is concrete, I will go here, I will go here, I will go here, hold it tight, and I can't go. So I'm holding it in a way that this is AY, by the way, the area of the cross section. This is the yield strength materials. This is the tension force. So area times the yield strength, how much tension force that I'm going to apply. That tension force, when I apply, keep increasing, still I will not able to remove it. I'm happy if this point will get tinier. I'm happy this point will going to reduce and it will start to stretch it. It will just try to stretch it, but this guy still holding it. You should not let it go. These guys still pulling. These guys try to small it down, so stretch, elongated, but still this one intact. I'm happy. That's how I want to design that. Stretch it and still this point is yielded. So that's what we're going to do it today. I hope it is makes sense. So this is what they explaining. That's what I explaining here. Now there are two kind of failures that will occur in the two or possible ways. One is concrete splitting at the location of the reinforcement, and shearing occur along the plane between the reinforcement and concrete reinforcement. So so let's say I will explain you the splitting first. What gonna happen when I have this bar inside and the concrete surrounding, the concrete start opening it up, is split, and it will try to let it go, right? You can look at this. These guys will give it up and they try to come out, not have enough strength. Then the concrete splitting might happen. I can explain you here in the physical stance that if I have too much force applying, then this concrete which is here try to split, try to open it up, because if I happens shearing occur along the plane of this one, so you have a shear force because you are trying to pull this one in this side. These guys try to hold it in that position, so you will have a shearing occurs in the region where you have a contact between the reinforcement and concrete. So there are two kind of things may happen, that you have a splitting and you have a shearing. Now splitting failures and pull out failures. How do the resistance gonna work? So let's say you have a resistance, right? Resistance meaning you have this resistance. Resistance meaning I will not let it go, right? This hand has a resistance, enough resistance to not let it go. That is the resistance. How much resistance you have is your how much concrete strength you have and how much length you are providing it. So this length, this length, if I have a less length, less resistance, look at that. I can pull it out. It's not that I'm not holding it, but it can easily, you can try by yourself in your home with the pen. But if I hold it more inside, I have more resistance. So that's what. And how much concrete compressive strength that you have around it. If it's more concrete compressive strength, more resistance. If it is a weak concrete, it will let it go, right? So that's depending on the concrete by the way, it's depend on the concrete tensile strength. So therefore it is FC dash. And development length I already explained you. So this resistance is area times FSY. What is that area? That area of this Rio times by the yield strength. So development land, how much land you need to provide to making sure that you will have a yielding that area. Just simplify that. That's maybe the splitting failures. This is the splitting failures, pull out failures. That let's say again resistance. I already explained you resistance. Now the is depend on how much tensile strength of the concrete and pi dB. So these parameters, that is pi dB diameter of your Rio times by the length. So that is the perimeters, how much perimeters that the reinforcement are covered. So you have area times FSY and you have FC dash pi dB. So you just simplify that, you might get the similar situation here, but that is the pull out failures. So you have two kind of failures. One is a splitting failures. The concrete around that one can split, and you might get the steel pulling out if you don't have enough development land. Now AS360 simplify this expression and combine them, but does not include several the same components. So what happens here? That you can look at these two ones. Let's say you have, because as an engineers, you don't know whether splitting gonna occur or pull out gonna occur. So you may ask questions, people, what gonna happen? Is it pull out or it gonna splitting? We don't know. So the standards makes our life easy, in the sense that it will give you the equation that will combine both of them. Let me find that equations, probably which clause that we are looking at. I think the 9 and I think about 13. Okay, yep. Close section 13. So section 13, stress development of reinforcement and tendons. So that's section 13, stress development and reinforcement and tendons. So they have give you this length, basic development length. This is the equations that we're going to. So this is the length. What is this length? This is this length. How much length you are putting inside the concrete, that is the development length. And there are factors. dB is the diameter of your Rio. Fy is the yield strength of your materials. Fc dash is the concrete tensile strength. It's square root Fc dash. This is the minimum development length, 0.05 FSY K1 dB. Some engineers smart, you know how they are. Like sometimes they will just muck around with the maths and said, I don't need development length. Just put the steel here, concrete here. Don't worry about it. Why? Standards telling me. Now the standards come back and smart play saying, regardless of your design, regardless of your concrete competency, whatever you do up and down, nitty-gritty things, I don't have bending moment diagram, I don't have shear, I don't have anything, I don't need development length. Stop. You must provide this minimum development rate, no argument, straight. So there is a minimum that you need to provide, regardless what criteria that you are following. So that's the minimum that you need to provide, and you can calculate and check against this minimum. If you are providing less than that, you just need to take it minimum. I hope it makes sense. So that's what I written on here. That and by the way, I will explain you these factors, each factors one by one. This K1, K3, and K2. There are 3 factors that I will going to explain you in these lectures and in the examples. Other factors I already explained you. And this is, by the way, the minimum development length that you need to provide, regardless of your any scenario that you are considering. So this is all good. Expression account, as I mentioned, splitting and pull out failures. Both failures will going to. So this is a pull out, by the way, as I explained you in the previous slide, that you will have a this steel Rio will coming out, or you have a splitting failures. That if you have a bar cover, you may your cover may split, or if you are providing that between the bar to bar, you might have a concrete between that is a split as well. So that is the a scenario that you might have a splitting, you might have this kind of a splitting, or you might have a pull out failure if you don't have adequate development length. Now this is a location to check the development length. Where is the important part of the development length, right? Let's take a cantilever. Cantilever means you have balcony. In the balcony, you have a tensile, you have a tension reinforcement at the top of the beam. And let's say we have person standing or some load apply at the end of that balcony. So if you draw the bending moment diagrams, you might get the bending moment diagram like this. You have a larger bending moment at this point. Now, someone might say that we can put the Rio and stop it here. No, that is very dangerous. What we need to put the reinforcement continuous by this end, from this end. How much we need to go in, the standards will gonna tell you. Sometimes you may not have enough room, then you can provide the cog and hook that I will come to you later. So we need to provide the additional reinforcement, and that is called development length, by the way. From this point to this point is called development length. How much Rio you should extend from that point, from the large bending moment, to have at this particular point we need to create the yielding in the bar. So therefore we have this one. So if you pull it out, how much you going, so you need that length, how much length you need to provide it so that you will have a ASTFY. And same thing here, you need to provide adequate length inside here in the members, and also you need to provide the adequate length on both sides. So you can see that you need to provide the development length that is passing from that point. How much development length you need to provide here to have enough, because this bar can pull out from here and this bar can pull out from here as well. So we don't need to pull out from any end. So from both ends, we need to provide enough development length such that it will have a yielding at this particular point. Oops, it's getting too big. Okay. All right. If you have a let's say simply supported, there's a cantilever. If you have a simply supported, for examples, let's say you have you terminate your bar here. Let's say you terminate your bar here. Then in that case, let's say you draw the line. You need to provide enough development length in this. You need to provide enough development length going inside, and you need to provide enough development length going on this side as well. So you can see how much that's on the left side, how much on the right side, that have enough development length such that it will create it will create the enough yield strength. It will create the yield strength at the points. Okay, this equation only use when you have tensile tension Rio. Where it is sitting? Close 13.1.2.2. I can show it to you. That is here on section 13, close 13.1.2 here. Development for deform bar in tensions, right? So when you have a tension, when you have a tension bar, you have tension Rio and you have compression Rio. So these equations particularly used in the tension Rio to create the yield strength in the tension Rio. Okay, I hope it makes sense. Now, first of all, let's work out the factor, each factor one by one. You have K1 factors. Factor K1. What is the name of the factor K1? Is written here. By the way, let me guide you first where it is. So K1 has two options. K1 can be taken 1.3 for a horizontal bar with more than 300 millimeter of concrete cast below the bar, or you can take K1 equal to 1. Standard does not give a name, by the way, and you don't need to remember this name, but K1 is called depth factors. K1 is a depth factors. What is depth factors? When you have, let's say when you have a concrete, so this is a Rio, by the way, this is tension Rio, okay? These both are tension Rio. When you have the reinforcement and you measure the concrete below the tensile reinforcement is less than 300 millimeters, right? The concrete which is below the below this tensile Rio is less than 300 millimeters, your K1 equal to 1. If your reinforcement which is greater than 300 millimeters, if your concrete sitting under the Rio, tensile Rio, then your K1 equal to 1.3. What is physically meaning that? So when your K1 equal to 1.3 and K1, so your 30% increase in the development land if you have a concrete more below your this one. So by the way, this one has require more resistance. So I can explain you this one. So if I put a concrete, if I have a steel Rio, and this depth, let's say I put it here, and this depth is let's say less than 300 millimeters. It here, right? You can see let's say 30 millimeters is just a cover. Let's say simply supported beam. Let me explain you in a more refined way. That let's say you have simply supported beam. Then your tensile Rio. Then your tensile Rio would be here. Right? Let me increase the. Then your tensile Rio would be here. Right? You with me? Then let's say this one would be let's say 30 millimeters. But let's say you have cantilever. Let's say you have cantilever and your tensile Rio is here. Right? So this is let's say 400 millimeters. Then your K3 value would be 1.3 here. You need to provide about 30% more development length here. You can imagine that, right? Because when you're loading it, this guy can easily come out, right? Easily come out, meaning that you need to provide more development length in the cantilever beam because your concrete below this one is 300 millimeters. Then the standards, look, this we follow US standards, 300 millimeters is a 1 foot. Someone said, where is this 300 millimeter coming from? It's just a 1 foot because they use foot units and we just follow the US standards. So we just said 300 millimeters. So when you have a reinforcement, then your K1 equal to 1, this development length, whatever you calculated, minimum development length, that will be enough. OK, I hope you understand the K1. Very simple. You have two options. You can take one, no effect on the development length, or you can increase the development length by 30%. It is a penalty, by the way. This is a penalty. When your tensile Rio sitting on the top of your beam or top of somewhere and you have a massive concrete sitting underneath, then your K1 equal to 1.3. If your concrete is tensile Rio is sitting at the bottom of your beam or slab or column, you might taking K1 equal to 1. Any questions in K1? Just unmute saying that, hey, Vipul, this K1 does not make sense. Thank you. Thank you for that, Joel. All right, so K1 looks good. Now let's move on. What happened here? Oh, K2. Now K2. What is K2? Again, this is tension, by the way. We are talking about tensions. Now K2 is called bar diameter factors. It's depending on your bar. Depending on your bar, meaning that, let me, if I have another, okay. All right, K2 has to do this one. Can you see the difference? I can put it this way. You can see the difference, right? Right, so K2 is what is the diameter of your bar? What is the diameter of your bar? What do you think? Should we put, let's say one beam has this bar diameters. Let's say you have a tensile. Let's say you have this, you have these diameters and you have another one beam, same beam and something, you have these diameters. Which one do you think require more development length? Is it a small one or big one? Because if I hold it, which one is more required development length? Put it in a chat or you can tell me. You understand my questions? Right? You have two options. Everything is same. All these FCDS, FSY, all these are same. Now the question is only we are changing small to big or big to small. Which one require more development length? Should I leave with this one or should I put this one? Or should I use just this one or should I put more here? Any clue? Equation is there, by the way. Let's check it. OK, look at this one. This is a development length. Development length equal to 0.058 FSY K1 dB. This is the diameter of your this is your bar diameters. If I increase this one, the development length will increase. Do you with me? This one, don't worry about, forget about, and here as well. This dB. If I increase dB, I need to provide more development length. Do you agree with me with, okay, maths you understand. Now come back to the practical. This one, if I have more, it's very hard to, so if I have a more, I can easily pull it out, right? So I need to provide a more development length here. If I have this one, I have more grip. You look at this, I can hold it in with this grip it and this one, so you don't need that much. But here, even I can't, you can't grip it because you have larger diameter. So for this one, larger diameters, you need to provide the larger development length. You with me? Because if you have, how can I explain you practically? If you so it's a logical that if you want to hold something big, then you need bigger hand. You need bigger hand. Otherwise, you need to provide this one. If let's say I want to hold this one. Let's say I want to hold this one. Look, there's a gap. I can't hold it that big, so I need to go more to hold it tight. You can see the larger the diameters, the more development length you need to provide. I hope it is makes sense. Any question? Unmute or anything. All good. All right. So K2, everyone understand that is a bar diameters. Bar diameter factors. In that sense, you can have equation 132 dB 100. Where is it? It's just sitting here. K2 132 dB over 100. Simples, very easy to find, and you just plug the dB value. So maths is very easy. I'm just also explaining the logic for this case. Okay. So you have this one, increase the bar diameters, decrease the K2 factors, K2 1 when the bar diameter is 32. So if you put 32 here, your K2 become 1. The small bar requires small development length. If you have more diameters, if you increase the diameters, you need to increase the development length. Okay, everyone understand K1 and K2. If anyone asks you and wake you up from your sleep and saying, here is the standards, explain me K2. It's not just reading. It's not just, what can I say? It's just not, you need to read between the lines. You need to have an understanding as well where this K2 coming from and what is their effect, whether it's going to increase or decrease, and not only increase or decrease, why is increasing and decreasing. That's also I'm explaining it to you that why these things happen. So I hope it is makes sense. Now K3. K3 is a cover and bar spacing factors, bar spacing factors. I think this one is a typo, just correct it. It's not a diameter factor, just the cover and bar spacing factors. So that is an equation for K3. I can show it to you here in the standards. K3 1 minus 0.15 CD minus dB on dB, and you need to check K3 should be between 0.7 and 1. So make sure that we need to make these checks. And CD is a dimension millimeter for so on in the figure. So look at this, that is your CD. CD would be minimum between these two bars. What is the spacing between this A by 2 or C1? What is the cover on the side cover or C, right? So if you put the bar very close to each other like this, then it will not good. It will going to crack in between, right? If you put the small cover here, the cover is very small here on the side, then it will be dominant, right? It will split. If you put the small cover here, so you need to find which one out of 3 would dominate the design. What dominant the design meaning which one going to affect first, who is the coming first. So that is this one, same thing here, cog and hook bars and so on. So it's very easy to read. A by 2 is the distance. A is, by the way, this is the face to face distance, not the center to center distance. Look at this. Okay, it's not center to center distance. All right, so that's simple to see. K3 is, by the way, you are providing the enough cover or not. you are providing the distance between one bar to another bar is enough or not. You're not putting the bar close to each other, so it will split. And CD is equal to A by 2 C, and I think I forget this C1, so put the C1 here as well. All right. So that's 2, 3 these figures. That if you have distance a by 2, if it is too small, then you will CD equal to A by 2. That's become, so that's what they're talking about. So when you pull out this bar, when you pull it out this bar, it will create this profile, right? The splitting profile or the concrete profile around it. So if you put close to each other, they will overlap on each other and it will crack on that one. So if the bar are too close together, tensile stress in the contact, interact, analysis, develop a overlap. So we don't want to overlap. We want to have this one. We don't want to overlap on each other, right? That is good. I'm happy. This one, not good, right? Penalty. Standard will apply the penalty for you. Now, if you put the bar too close to the surface, so let's say someone put this, let's say someone put this bar very close to here, then when they create the profile, it will going to crack. Not good. If someone put the bar which is far from the surface, this is good. I like it. This one, so standard also like it. So standard wants you to do this one. If someone put the very close to here, then this will do this. Not good. You can have a like this, enough distance from here to here, enough cover, then this is good. So that's what it's explaining here. And we will use the maths to identify which one is we have it problem one. Is it the bar to bar, meaning one bar to the next bar is causing the trouble, or we are putting the bar close to the side and that will causing the trouble, or we are putting the bar next to the bottom surface, so that is causing the trouble. Okay, bar cannot develop the full strength, as I mentioned. This is not good. Now sometimes meaning that, let's say you don't have enough room, as I mentioned before, that you have, let's say you have this cantilever. Let's say you have this cantilever beam, and you have this, and then you have this. Let's say you have this wall. Now we want to put the Rio. We want to put this Rio, and someone say that I want, let's say I want this 300 millimeter of development length from here to here. But someone said, your architecture said, no, you have only 150 millimeter of wall or something that you can use the development length. So what the standard is saying, that you can use the the cog and hook. So hook is 180 bend. So this is your hook, standard hook, and this one, so this is 90 degree, meaning the cog, and this 180 degree is your hook. Now in here, what you can do, you need 300 millimeters, so you can either use this, cog, or you can use the hook, and then you can reduce by 50%. So you just need to have it. If you have a 130, you can reduce by 150. Here also you can reduce by this 50%. So and it's always good idea to have this cog and hook, because it will provide more mechanical anchorage. As you can see, they are providing more mechanical anchorage offered by the band, right? So yeah, it is a good practice to use the hook and cog. One on the one hand, if you don't have enough room, it's allow you to create the enough development length. If you don't have enough room, then you can use this cog and hook. Okay, for compressions, as I mentioned, you have a compression Rio as well, right? It's not always you just need to have a tensile Rio. So you can use these equations. Probably I can show it to you here, the compression one. So the compression one is development length bar in the compressions, and you can see these equations: 200, 0.2 FSY FCDS dB, 0.0 FSY dB, or 200, whichever is greater. So this is a minimum. Minimum you need to provide 200. And the detail about the standard hook and cog, I already explained you, 0.5 LSY. Okay, so that is the cog and hook that I just explained you. Now, must not be used within the development lengths. So now, together with the continuous and the development length in the compression is much shorter than tensions. As you can see, the compression is not a big troublemakers. Tension is the one that will going to be troublemaker. So you need to provide more length in the tensions. The development length on the tension side is more than the compression side. Compression side is not that much. So you have some soft one. You remember that we have about 300, 200 millimeters or from this one. For deform bar, the basic development length, I already show it to you in the standards. Hook and cog must not be used within the development length. So for this case, we don't want to use this hook and cog for this development length. You may use the bundle bars. You know the bundle bars. Bundle bars meaning that you will have a you can make it 4 bars bundled together. So let's say you have 4 bars. I think close 13.1.7. Let me go back there. 13.1.7. Yep, development length of bundle bars. The development of bundle bar shall be development require largest of the bundle increase. So you just need to have if you're using 3 bars bundles, you need to increase by 20%. And if you are using these ones, probably you can't see it. Now you can see it. So you need to, if it's 3 bar, increase the development length. You just calculate the development length for 1 bar. Just calculate, the diameter of your bar. When you make a bundle bars, you need to know what is the diameter. Let's say you have a bundle bar like this, not a different bar Rio, but you have these 4 or 5. Then you take a 1 Rio and you calculate the development length for the 1 Rio, and then you increase by 20% when you have a 3 bar bundle, and you can increase by 33% if you have a 4 bars. So I hope it makes sense. So this is 1.2. As I mentioned, you have a 20%, so you just multiply by 1.2, whatever you get, or you can increase by 30% by multiplying 1.33 if you are using the bundle bar. So I hope it is clear. Bundle bar is not super complicated. If you just calculate you just treat that bundle bar as a 1 bar. And as you know, the diameter, the bundle bar is bigger, so you need to provide the extra development length. As I mentioned, diameter increase, and if you're considering the bundle bar as a diameter of 3 times or 4 times diameter of the original bar, you might want to provide the larger development length, and that larger development length comes from 20% or 33% of the development length. Any questions so far? Development length we finished. Laplant. What is Laplant? For wide element like slab, wall, and flanges, tensile Laplant can be calculated by using this one. So I can show it to you here. What is Laplant? Because sometimes when you have a bar like this, and there is another bar, because you can't have a bar which is continuous and then say there is another bar here as well that you need to continuous, right? So what you can do it, you can tie them together. You can hold them together. So that is a Laplant. How much length you need to overlap? Let's say LSY dot T lap. I hope you understand that Laplant, that how much length you need to provide that will transfer the stresses from one bar to another bar, right? I can explain you physically. That will make more sense. Let's consider they are the same size. Okay, so you have this bar and you just need to continue because you can't stop it. Let's say there is not enough length, then you just put another bar on here. You can use the wire to tighten it up this one. You can use the another wire to tighten it up this one. So how much length you should lap? How much length you should lap, either this one or that small or that big? How much length you going to lap? So when it subject to the tensile force, it will have a same force transfer from this one to this one. So I hope you understand. So that is a lap length from this point. Let me put it on here. So from this point to this point, that is the Lapland that I want to experience for you. So and that Lapland is given, I think, where in clause 13.1.13.2.2. So here you go. Splicing, I think they call it splicing of the reinforcement. You can read about it. And lap splice for the bar in tension. So that is the tension, by the way. When you have a tensile bar, you have K7, LSTY. This is a minimum lap length that you need to provide. I think this is a minimum. As I mentioned, you might, as I mentioned, some smart cookies, they might say, I don't need to provide. Let's do this one. Why? I done K7 equal to 0 or LSYT equal to 0. Then standard said, but this is not greater than the minimum. You need to provide this minimum lap length regardless of your design. So that's the minimum that you need to provide. All right. So lap length LY develop the length on clause 13.1.2. So we can calculate the development length and we just multiply by L7. Sorry, K7. Now K7 is 1.25. If your AST, the tensile Rio is less than your 2 times the required one, or you can use K7 equal to 1 if your AST provide is greater than 2 AST required, right? I think that is given in the standards, by the way. It's not the one I'm making it up. So K7 shall be 1.25 unless AS provide at least twice the AS required, no more than half of the reinforcement at the section is spliced, in which case K7 must be taken as 1. Right? That's what I explained in a simple format. All right. For beam and wave columns, tensile lap length is maximum of this one, maximum, or I think this is should be plus. Okay, this maximum of this one, or maximum of this one, or maximum of this one, right? So I can get it somewhere. Here you go. For narrow elements or members such as beam, wave, and column, tensile lap length shall not be less than the larger of this first one, second one, and third one. That's what I just, it's given in the clause 13.2.2 lap splice for the bar in tensions. So that is, so SB is a clear distance between the bar in the lap splice. So SB would be 3 or SB equal to 0. Now splice for fully stressed bar that are lap splice and is closely proximate, the lap length must not be less than, I already explained you this, lap lengths. All right, I think I need to explain this one. There are clause 13.2.2. You can see these figures. These figures are a little bit complicated. Look at these figures, like 100% bar splice, no stagger splice, and you have 50% stagger splice. It's a little bit complicated figures. I need to explain you that 2 figures here. That let's say you have this bar here, and there is another bar which is tied together. Right, there is one more bar, and there is another bar which is tied together again here. You have one more bar and one more bar here that is tied together here. That figure is given here. This one here. That you have a bar, you have this bar, you have this bar, you have this bar, you have 100% bar splice, no stagger splices. So that's figures I explain you here. So in that case, your LSTY lap is 1.3 of LST. So LYST you can calculate. You remember that equations. You remember that K1 and K2 and K3. We use that equation. So you can have 1.3 when you have these situations. This L splice, you can calculate this L splice in these situations by taking 1.3 or greater than or equal to 300 millimeter. That is the minimum. 300 millimeters is the minimum. You can't go less than 300 millimeters. So that is minimum, or you can have this 1.3 LYST. Now 50%. So look at this. Is a staggered. Okay, so you have this bar here. You have another bar here. You have one bar here, another bar here. Then you have this bar shorter and this bar here. So you see they are not in the one line, right? You can see this one in the one line. 50% of splice require lamp length. So only 50% bar fall in the required lamp lengths. If you take this lamp length, then only 50% will fall here. If you take this lamp, only 50% because it's a stagger. In that case, you can take LYST is 1 times LYST greater than or equal to 300. So the standards provide a higher penalty here, 30%. Standard don't like this one they like it, the way that you put it in that format, and that is by the way given here. So this one you can look at this, look at this, look at this, look at this. So that's a stagger one, 50% one. All right, stirrup and fitment. Sometimes those stirrup and fitments provide the confinement. You know, these stirrups that if you have a tensile Rio here, these stirrups will help you. This is our friend. Why? Because it's going to hold it, this guy here, right? It will going to what can I say? It will try to. It is our friend because you. Let me show you. Oh, okay. So look at it. Let's say this is tensile Rio, and this is the. You can see this. We provide this what we call this 90. Cog is a 90 degree, so this is a 90 degree, so that you provide this 90 degree cog. Now here, if I have these stirrups, you look at that stirrups, right? And those stirrups going to hold these wires in the position. So it is our friend that it will even give you more grippings. As you can see, these guys are going to hold more, and it will provide the confinement in the concrete. So this concrete will be confined in here. So this is our friend. That's what the standards will going to tell us, that if you have to be properly effective, the fitment should be enclosed and longitudinal, preferably with a hook. Okay, so that's fine. Fitment should ideally be continuous on the tension side of the beam, and therefore in the zone negative bending down and open fitments as shown upside down or closed fitments. So they said that use the closed fitments. It will help you to reduce your development length. Okay, now next one. It's not always the standards want you to keep increasing the development length. It's not standards telling you that okay, you keep increasing your development length. You can use the curtailments. Now curtailments is the bar that you cut it off. Cut it off meaning you don't need to provide the additional bar that's not required because of the demand from the bending moments. Let me explain you that one. Let me tell you that. Okay. Let me tell you. Okay. Let's say you have this is simply supported. Let's take a simply supported beam, and you have a UDL load on this concrete beam. So if I draw the bending moment diagram, then the bending moment diagram would look like this. Do you with me, right? This is, let's say, M star. Now, for this beam, which is sitting here, let's say you provide 4 bars. Let's say you provide 1, 2, 3, 4 bars. Now these 4 bars you provide because you are designing it for maximum moment M star. You with me? Because these 4 bars that will useful in this zone. Let's say you need 4 bars here because you have higher one. But what about these guys here? Look at this. This is very tiny moments here. This is very tiny moments here. These moments are very small. You don't need 4 bars here. So standards allow you to make the curtailments. As I mentioned, the standard saying that, okay, guys, you can cut it off your bar when your moment is less. So you can let's say 50% moment. So let's say you have 100 kilonewton moments here. Then when you reach 50 kilonewton moments, you can cut it off your bar. So you don't need 4 bars, you might need 2 bars. But you need to extend for the development length, so you can practically cut off here, right? So that's what this curtailment saying, that at this end you might need only 2 bars. So for examples, if you have a beam, let's say this is top view of the beam, you provide this let's say this is the ideal situation, 4 bars. But let's say, for examples, if you want to theoretically cut off, then you can just have it cutting it off of this one, right? So that's the situation, saying that okay, when you have a bending moment is at 50%, you can cut off your bars, right? So that is called curtailments, and I will tell you where the standards let you cut off that bar. So a simplified approach to the curtailments where live load, the condition is that live load should be less than the dead loads. Okay, when you have these situations, you can use clause 8.3.1.5. Let me take you through the clause 8.3.1.5. By the way, I'm just 8.3.1.5. Here you go. 8.3.1.5, negative moment tensile reinforcement provided at the support, and positive bending moment reinforcement provided at the mean spot. So these two clauses that I'm going to explain you using the figures. So what happens here? This one, let's say you have this support here. This support is here, and you have another supports here. So if I draw the bending moment diagrams, you have a bending moment diagram look like this. Okay, so positive bending moment here, negative bending moment here. So at the negative bending moments, you need to provide the top Rio, right? You with me? So here you have a negative, so you have top Rio here. Now for negative bending moment, we have top Rio. So what the standard saying that you need to provide you calculate the AST. So you calculate this top Rio and you have AST. So you need to continue all your bars greater than or equal to 25% from this end to the. You can't do the curtailments. You need to provide at least 0.25 AST. So let's say you have a 100 millimeter square area, then you need to continue 25 millimeter square from this end to this end, right? So there is no any options. You need to provide at least 25% of your AST at the top. Now you can reduce by 50% reinforcement that you need to provide from the support to the 0.3 ln, and ln is the just the distance between the face of the support. So 0.3 lns, you need to provide at least 50% of your AST. So if you have 100, you need to provide 50 millimeter square. And in this zone, from 0.2 to ln, from here to here, 0.2 to ln, you need to provide the full AST. So I hope you understand the curtailments. The curtailment saying that, and this all the details are given here in this clause, saying 1/4, 0.3 ln, 0.2 lns. That's what I explained you in the figure. That's in the negative moment zone. When you have a negative moments near the supports, you can provide the full 0.25 AST in the full. No any compromise. You can't provide the curtailments for 0.25 AST. You just 20. But in the 0.3 lns, you just provide the 50% AST, and in the 0.2 lns, you provide the full AST. Similarly, you can do the you can have this positive bending moment. So let's say I redraw this one, support here, support here. You have a UDL load on the beam. And then if you draw the bending moment diagram, it would look like this. So you have positive bending moment here. This is negative bending moments. And we're done with negative bending moment. Now positive bending moment at the midspan. So we have positive bending moment here. In the middles, you need to provide the full AST. Can provide the full AST in the middle because we have very high moments. Now, from the face of the support to 0.1 ln, you need to provide at least 0.25 AST. And similarly here, you need to provide 0.1 ln, you need to provide 50% of AST. Again, these all the details are written here. That positive bending moment, not less than 1/2 extending into this one, 12 dB cog, not less than 1/4, and this all written in this one. So I hope you understand the curtailments as well. Now there is an examples that we're going to cover. An example is very simple, but let's have a drink before we start. But just tell me if you have any questions. Some students don't know it. Probably they got the drill, or they have some other commitment. Some are holding it up. Let me know if it makes sense or completely out of track. All good then. Let's turn off this and let's just use this one. I hope you can see the screen. All right. So calculate the development length for 3N24 straight top bars. So you have 3N24 straight top bars is 600 millimeters by 300. Sorry, this one is 300 millimeters. Correct it. The cover is 36 millimeter on the top. So you have cover here 36 millimeter top, 40 millimeter on the side, 40 millimeter side. FC dash is given 25 megapascals. Right, so that's details are given. We need to calculate the development length. Now the development length is, and by the way, there are two. I think in the workshop I will cover the second one, but the first one, they are 13, section 13. I did not cover in my lectures, but I think we will take an examples just for your information. So we have a basic development length that is 13.1.2. We're going to focus on this one first. Then you have refined development length. Refined has more calculations. You might reduce your development length by sometimes. So you can have additional calculation. Well, probably in the workshop we will take this refined development length. It's nothing. It's just addition. I think the refined development length they will take into account this one, like the refined one. They will say that you have a fitments. If you have fitments, then we will just have to have a refined development length. But this first one, they don't take into account the confinement and the contribution coming from this fitment. So that is just a basic. The difference between, as I mentioned, basic development length and refined development length, that they don't take into account. This one account transverse reinforcement. This one don't account that one. But anyway, that's this one is the basic ones for our course is good enough. Let's continue. So the equations that we're going to take it is this. LSY TB. TB is the basic development rate, 0.5 K1 K3 FSY DB, K2 FSY, and we're going to have a minimum one here as well. All right, now let's put it in the notes. So let's put the two equations. Minimum development length L SYTB, let's put it minimum, equal to 0.058 FSY K1 dB. By the way, this 0.051 is FSY is 500. If I put it in the calculators, 0.058 times 500, you get 29. So it's like this 29 K1 dB. In other words, the standards just oversimplify that, but I think this is just a 29 KB dB. Actual real one, LYS equal to 0.5 K1 K3 FSY dB dB per diameter over K2 FC dash. Okay, so let's get the factor one by one K1. And by the way, this one given in the close 13.1.12. Now K1. What is K1? K1 is called, I think we call depth factors. Let me put the K1 is depth factors. Let's say depth factors K1 equal to. Now here K1 has two options. K1 can be 1.3 for horizontal bar with more than 300 millimeter of concrete cast below and the bar, or K1 equal to 1. So let me go back and check. I think we have 600. So if I calculate this one, that would be greater than equal to 300 millimeters. So we in this category, we have more than 300. So K1 equal to 1.3. We are here greater than 300. K1 equal to 1.3. So you with me that K1 equal to 1.3. K2 is called K2 is the bar diameter factors, and that is the equation 132 dB 100. Bar diameter factor, and that is K2, and that would be 132 dB over 100. What is our tensile real? Is 24. Right? So let's say we plug the 24 millimeters there. Yep. So let's plug the 24 millimeters. 132 24 millimeters over 100. So 132 take away 24 over 100. You need 1.08 K2. K3. What is the name of the K3? K3 is equation here, and the K3 that we're going to take it cover and bar spacing factor. Cover and bar spacing factor, K3, and the equation for K3 equal to 1 minus 0.15 CD minus DB over DB, and that is 1 minus this, and we need to make a check that it should falls between 0.7 and it should falls between 1. So let's say DB, we know the bar diameter is equal to 24 millimeters because we have given N24. So we have 24. Now CD we need to calculate. Now for the calculation of CD, we have from options narrow element or member, beam, waves, and columns, and wide elements of member, flange, band, beam, slab, walls, and the band. So we need to have a beam, waves, and columns. So I think we are here in these situations like this. We don't have we have straight bars is given in our examples. So minimum of A by 2, C1 and C. Minimum of A by 2, C1 and C. Now let's do the C1 is a side cover and C is a bottom cover. So C1 equal to side cover. How much the side cover is? Side cover is 40 millimeters. So you have 40 millimeter side cover. C is a bottom or top cover. So we have a 36 millimeter top cover. So C is equal to top cover 36 millimeter. Now A by 2, we need to calculate A by 2. So we need to calculate a distance from here to here, that is the A. Let me draw it up. That I think we have 350. I think there is a typo here, 350. So let's say you have from this end to this end is 350. You with me? And you have 4 bars. 1, 2, 3, and 4 bars. And each bar is 24 millimeters. You with me? 24 millimeters, 24 millimeters, and 24 millimeters. Cover is 40 here. Side covers. I can show it to you here that the cover is 40 millimeters on the side. So we need to calculate this A distance A. Right? That is by the way given here. That is given here, face to face distance A. Now, if I want to calculate A, 350 millimeters is equal to 40 millimeters, this first one, plus 24 millimeters, that second one, plus A, plus the second 24 millimeters, plus A, plus 24 millimeters, plus A, plus 24 millimeters, plus 40. I hope you got it. So if you simplify that, you will get 350 equal to 152 millimeters plus is it how many bar we got? 4 or 3? Sorry, I think we just make it 4 bar. We don't have 4 bars, we have 3 bars. So let's draw it up again. 1, 2, and 3 bars. That's okay. 40, 24, A, 24, A, 24, and 40. So let's make cancel this. So we have 40 millimeters, this first one, plus 24 millimeters. The second one, plus A, plus 24 millimeter, plus A, plus 24 millimeter, plus 40. So you get 2A, 350 millimeter, take away 152 millimeter over 2 equal to A. So A you will get 99 millimeters. Now we have all the values to calculate CD. Now CD is equal to minimum of A by 2, C1 and C. Minimum A by 2, 99 divided by 2. C1 we calculated 40 and C is 36. 40 and 36. So 99 divided by 2, you get 49.5. So the minimum would be 36. You can look at that. This cover that is on the top is going to be critical one, this one here. So in that case, we can calculate K3. Let me write down the equation again, K3. 1 minus 0.15 CD dB over dB. 1 minus 0.15 CD 36 millimeter, dB 24 millimeters over dB 24 millimeters. We got 0.925. So I think we got everything to calculate this development length, basic development length. So basic development length LSYTB equal to 0.5 K1 K3 FSY dB over K2 FC dash, and that is square root. So 0.5 K1 we calculated first was 1.3 and 1.08 K2. 1.3, 1.02 K2. Concrete compress is 1025. I can show it to you. Concrete compress is 1025. And the K3 we got just now is 0.925. 925. Yield strength 500 megapascals. 24 millimeter is the bar diameters. So we got 1336 millimeters. And minimum LISTB equal to 0.058. I think, by the way, that 0.058 is just a 29 K1 dP. 29 K1 dP. 29. I think K1 we got 1.3. dB is 24 millimeters. So that in that case we will get 904.8. Since our calculated LSYTB equal to 1336 millimeter is greater than LYSTB limit or minimum, which is 904.8 millimeters. Therefore, it is okay. So we can use LSYTB equal to 1336 millimeters. We generally don't, we just use the rounding off error, rounding it off, like 13, like 1350 millimeters. All right, so I hope you understand that the development length. So they just say that, okay, if you have they have a tables, you know, Rio data tables, right? I think it's this one. And yeah, look at this. They have these tables. They might have updated, but this one based on 2009. They have all these bar diameters. They provide LSYTB. Even they provide the lap length as well. There is a table that you can really use, but you know how to use these tables as well now. Is a class classification, A1 classification, you know, durability, A1 classification and A2 classification and B1 classification and so on. So they use this 29. You remember this minimum and K1, K2. I think there are we use latest one, but yeah, they have this one. I think I think there is a, you remember there is a conjunction. Probably they have these couplings. Couplings meaning that you know, sometimes when you have a bar, it is too conjuncted. It would be too conjuncted to have this Laplant. Sometimes they have a coupling. Coupling meaning that is a mechanical coupling that can couple both your. It's readily available in the market, so you don't need to provide the Laplant. You can just have a coupling, and coupling is very strong. They might have a coupling, sure. Or I can find the coupling for you. No, they don't have. No, they don't have a. Yeah, something like this. Look at this. These guys here. You can connect to Rio by using these couplings. You can see these couplings. I think in our look at these couplings. I think in our guest lectures they covered.